weird sets.
So let's now that we have in our hands the sample space and the probability law, we can actually solve any problem there is. We can answer any question that could be posed to us. For example, what's the probability that the
Oh, come on.
outcome, which is this pair, is either 1 or 1, 2. We're talking here about this particular event, 1, 1 or 1, 2. So it's event consisting of these two items. According to what we were just discussing, the probability of a finite collection of outcomes is the sum of their individual probabilities. Each one of them has probability 1 over 16. So the probability of this is...
Why doesn't this always work?
So it's an event consisting of these two items. According to what we were just discussing, the probability of a finite collection of outcomes is the sum of their individual probabilities.
Probability of a finite set of outcomes is equal to the sum of their probabilities. So like probability of 1, 1. It's a set of finite outcomes. Set of finite outcomes. So you can do this because this is a finite set of outcomes. You can only do this because it's a finite set of outcomes. One over 16 plus 1 over 16. Is that on the previous slide where he basically says that the probability of an event E is equal to the sum of all the outcomes in E, the probability of that particular outcome? So this only works for, I don't know, this only works for like finite / discrete sample spaces, experiments. Is this on the previous slide?
One of them has probability. That the it consists of
yeah, it's right there.
Elements. Now,
come on.
Finite set I can write as a union of single element sets.
Serious? So why isn't this stupid thing working?
I can write it as a in this picture of 3 elements. In general, it consists.
Okay, so there it is. It's right there. If it's a it doesn't really specify here that S1, S2, SK is from like a finite experiment, because like this could be like a continuous probability distribution. This could be a continuous sample space, could be a continuous experiment, and this would not hold. With the Dart example, you can't just Well, actually, I'm kind of confused with the Dart example. Maybe it does hold, where if you just kind of like list out finite events. I mean, like on the Dart, if you said, all right, what's the probability of this, of like this finite set of these 5 points? Well, it's 0. So, but that's a weird way to, I guess you can really only talk about probability of events in the continuous case when it's not equal to 0 by kind of like, I don't know, specifying some area range thing. You can't just specify individual points. Come on.
Of k elements. Now, a finite set, I can write it as a union of single element sets. So this set here is the union of this one element set together with this one element set together with that one element set.
That's true.
So the total probability of this set is going to be the sum of the probabilities of the one element sets. Now, probability of a one element set, you need to use the brackets.
Yeah, he kind of skips the step where, I mean, he just explained that, but he said like the probability of S1, S2, SK, this is equal to the probability of S1 unioned with S2 unioned with SK and I don't know if he, I guess this is maybe on like a previous slide, but if you say like the probability of two sets like A union B and A and B are disjoint, then this is equal to the probability of A plus the probability of B. I mean, in the general case, it's equal to the probability of A plus the probability of B minus their intersection. You don't want to double count their intersection. But if their intersection is 0, then you can just chop it off. Yeah, I don't know if there was somewhere where he specified that. I mean, he defines events right here, and he's actually defining like probability on this slide. So there's nothing before this. Oh, okay. Okay, no, he's saying right here. Okay, if A intersect B is equal to 0, then the union, okay, is equal to adding those up. Okay. Okay, so kind of going back to that then, kind of rewriting it. Yeah, you have the probability of S1 union S2 union and so these are all individual outcomes and they don't intersect at all. So this is just the probability of, yeah, it's basically just S1 plus S2 plus, yeah, it's basically that. Okay.
Sure, because probabilities are assigned to sets, but this gets kind of tedious. So here one abuses notation a little bit, and we get rid of those brackets and just write probability of this single individual outcome. In any case, conclusion from this exercise is that the total probability of a finite collection of possible outcomes, the total probability is equal to the sum of the probabilities of individual elements. So these are basically the axioms of probability theory, or, well, they're almost the axioms. there are some subtleties that are involved here. One subtlety is that this axiom here doesn't quite do the job for everything we would like to do, and we're going to come back to this at the end of the lecture. A second subtlety has to do with weird sets. We said that an event is a subset of the sample space, and we assign probabilities to events. Does this mean that we are going to assign probability to every possible subset of the sample space? Ideally, we would wish to do that. Unfortunately, this is not always possible. If you take a sample space such as the square has nice subsets, those that you can describe by cutting it with lines and so on, but it does have some very ugly subsets. If going to find a probability law. There's lots of possible. Now we need to assign a probability law.
Probability law.
There's lots of possible probability laws that you can assign. I'm picking one here arbitrarily, in which I say that every possible outcome has the same probability of 1/16. Okay, why do I make this model? Well, empirically, if you have well-manufactured dice, they tend to behave that way. We'll be coming back to this kind of story later in this class, but I'm not saying that this is the only probability law that there can be. You might have weird dice in which certain outcomes are more likely than others. But to keep things simple, let's take every outcome to have the same probability of 1/16. Okay, so let's now that we have in our hands the sample space and the probability law, we can actually solve any problem there is. We can answer any question that could be posed to us. For example, what's the probability that the outcome, which is this pair, is...
These are all individual outcomes. Outcome, 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 outcome. This is the sample space. This is the outcome, 1, 4, basically. This is the outcome 4, 1. This is the outcome 3, 3.
1, 1 or 1, 2. We're talking here about this particular event, 1, 1 or 1, 2. So it's an event consisting of the two items. According to what we were just discussing, the probability of a finite collection of outcomes is the sum of their individual probabilities.
Just always breaking it down to the most simple thing.
One of them has probability 1/16, so the probability of this is 2/16.
So just kind of writing it out, it's like
probability 1/16, so the just discussing.
So the probability
of a finite.
Probability of so it's basically the event 1, 1, 1, 2. What's the probability that this event happens? Well, these are two outcomes here. Outcomes don't overlap. So it's equal to the probability of 1, 1 plus probability of 1, 2, which is equal to 1/16 plus 1/16. Do this because you've got these outcomes. Probability doesn't say anything. It doesn't even say anything about outcomes, kind of. It just talks in terms of sets, an event, do they say an event is a set of outcomes? Is that how events are defined?
Two items. According to
This thing, a subset of the sample space. Event is a subset of the sample space. And so what is the sample space? I think it said the sample space is the set of possible outcomes. Pretty sure that was said. It's how like the sample space was defined. Sample space, set of possible outcomes. Okay. And so when we say an event is a subset of the sample space, then kind of by transitivity, I guess, we're saying that an event is a set of outcomes. Okay. An event is a subset of the sample space. You basically say an event is a subset of the sample space and the sample space is equal to the set of outcomes. Implies that the event is a set of outcomes.
because
Just keep keeping this in mind, that really we're the kind of atomic units that we're dealing with here are the sample space, and we have outcomes, and events are kind of up from there. Kind of way we drew it last time was that sample space and events were kind of at the second level, and then we kind of brought it back to outcomes like that. These are the three things we're dealing with, and probability is defined at this level. Probability of an event. Dealing with sets. Intersection is empty. Intersection is empty. Then the union of the two events is just the things added.
obey those properties, then you can go ahead and do useful calculations and do some useful reasoning. So what are these properties? First, probability is saying that the probability of omega is equal to 1. Pretty...
Yeah, even that, I think it's really useful to even just kind of look at this, be like, the probability of omega is equal to, well, omega consists of all the events. So it's the probability of O1, O2, On. So these are all outcomes. So I don't know, whatever. It doesn't even matter that they're not outcomes. We can just rewrite any set as kind of like all its elements union together. Okay. And yeah, these don't have any overlap because they're just elements. So yeah, it's equal to the probability of O1 plus probability of O2 plus ON. And it actually took this as an axiom. So we can't actually show this. Like, this is just assumed. So, but if this is an axiom, then like this whole thing has to add up to 1. So if you just take like any of these, you say like the probability of the first outcome is equal to 1 minus probability of basically like the sum over all the other outcomes. It's like the sum over all the outcomes such that O is not equal to O1 of probability of O sub I. Yeah, I just O, I guess, for loop. How do you write this? The probability of O such that O is in sample space and O is not equal to O1. Axioms. Every subset has to be greater than or equal to 0. Probability is assigned to an event.
Straightforward so far. The more interesting axiom is the third rule. Before getting into it, just a quick reminder. If the probability of A plus the probability of event consisting of three pieces. And I want to say something about the probability that you can is equal to 1. Notice the syntax that's being used here. Probabilities are assigned to subsets, to sets. So we think of this as meaning the set of all outcomes such that x is equal to 1.
Set of all outcomes such that x is equal to 1. So x is here. Set of all outcomes such that x is equal to 1. You've kind of got all these outcomes, and you kind of want to look at the outcomes like 1 star. So yeah, it's all these. So I guess there's 4 of those.
How do you answer this question? You go back to the picture and you try to visualize or identify.
Kind of look it up and say that the probability of x equals 1 is equal to the probability of, we got 1, 1 in there. We got 1, 1. We got 1, 2. We got 1, 3. We got 1, 4. And so it's just equal to the sum of those. So it's just, 1/16 plus 1/16 plus 1/16 plus 1/16, 4/16, 1, 4.
Event of interest. X is equal to 1 corresponds to this event here. These are all the outcomes at which x is equal to 1. There's 4 outcomes. Each one has probability 1/16. So the answer is 4/16. Okay. How about the probability that x plus y is odd. Okay, that will take a little bit more work, but you go to the sample space and you identify
X plus y is odd. So what are all those outcomes? So we have 2, 1 here. We got 4, 1. We got 1, 2. We got 3, 2. We got 3, 4. We got 2, 3. We got 1, 4. We got 3, 4. The probability that x plus y is equal to 1 is equal to the probability of, we got 2, 1. We got 4, 1. We got 1, 2. We got 3, 2. We got 2, 3. We got 4, 3. We got 1, 4. We got 3, 4. Which is equal to the probability basically of 2, 1 plus the probability of 4, 1 plus the probability of 3, 4, which is equal to, basically 1, 2, 3, 4, 5, 6, 7, 8. 8 over 16 is equal to 1/2.
all the outcomes at which the sum is an odd number. So that's a place where the sum is odd. These are other places. And I guess that exhausts all the possible outcomes at which we have an odd sum. We count them, how many are there. There's a total of 8 of them. Each one has probability 1 over 16, total probability.
Just realize you can kind of reason geometrically as well, because if you kind of like rearrange all these all these colored in spots, then it would kind of look like half of the thing is colored in. So the whole sample space has to add up to 1. So it'd basically be 1/2. And in the case of the first one, 1, 1 or 1, 2 like this, you kind of count up of the whole sample space. If you just kind of looked at it, like this whole row would be 1/4, but it's like half of this row. So it's kind of like half of 1/4, which is equal to 1/8, like that. And so the probability that x is equal to 1, you basically got all these. And you can basically just reason geometrically that, this thing is 1/4. If you wanted to, you can kind of split it kind of in half and say, all right, this is half here, and then this is half of the half. So this is 1/4. It's reasoning geometrically.
It's 8 over 16. And harder question, what's the probability that the minimum of the two rolls is equal to 2?
The minimum of the two rules is equal to 2. It's equal to 2. So you basically have the minimum. Okay. So you basically got 2. You basically got 2 and something greater than 2. Or you've got something greater than 2 and 2. So if we fix the first one at 2, then we look at what's greater than 2, basically these two here. And if we fix the first, maybe how about let's fix the second one at 2 and what's greater than 2. Seems like it's these 4 right here. So if we kind of reason geometrically and kind of like pop these down to this, we notice that we just have one row here, and so should be equal to a fourth.
Something that you probably couldn't do in your head without the help of a diagram. But once you have a diagram, things are simple. You ask the question, okay, this is an event that the minimum of the two rows is equal to 2. This can happen in several ways. What are the several ways that it can happen? Go to the diagram and try to identify them. So the minimum is equal to 2 if both of them are 2's.
Okay, I guess I missed that part. It's like the minimum is 2. So you basically got like, yeah, so you basically got.
Or it could.
Yeah, so you basically got the same argument where it's like it's 2 or it's greater than or equal to 2 or it's greater than or equal to 2 and it's 2. So if we fix 2 here, anything greater than or equal to 2. And then if we fix this 2 here, it's anything greater than or equal to 2. So this one's a little more, so we basically got, you know, if we pop this one down here and then like this is just one left over. So it's basically 4 over 16 plus 1 16th. It's like 1/4 plus 1/16. Yeah, it's just 5 over 16.
Can happen. Go to the diagram and try to identify them. So the minimum is equal to 2 if both of them are 2's. And, or it could be that x is 2 and y is bigger, or y is 2 and x is bigger. Okay, I guess we rediscover that yellow and blue make green. So we see here that there's a total of 5 possible outcomes. The probability of this event is 5 over 16. Simple example, but the procedure that we followed in this example actually applies to any probability model you might ever encounter. You set up your sample space, you make a statement that describes the probability law over that sample space, then somebody asks you questions about various events. You go to your pictures, identify those events, pin them down, and then start kind of counting and calculating the total probability for those outcomes that you are considering. This example is a special case of what is called the discrete uniform law. This model obeys the discrete uniform law if all outcomes are equally likely. It does.
I feel like this is this discrete uniform law. I feel like it should be like the discrete uniform, like corollary or theorem or something. I feel like a law seems to imply that it's like an axiom. I don't know.
Have to be that way. That's just one example of a probability law. But when things are that way, if all outcomes are equally likely, and we have n of them, and you have a set A that has little n elements, then each one of those elements has probability 1 over capital N, since all outcomes are equally likely. And for probabilities to add up to 1, each one must have this much probability. And there's little n elements that gives you the probability of the event of interest. So problems like the one in the previous slide, and more generally of the type described here under a discrete uniform law, these problems reduce to just counting. How many elements are there in my sample space? How many elements are there inside the event of interest? Counting is generally simple, but for some problems it gets pretty complicated. And in a couple of weeks, we're going to have to spend the whole lecture just on the subject of how to count systematically. Now, the procedure we followed in the previous example is the same as the procedure you would follow in continuous probability problems. So going back to our Dart problem, we get a random point inside this square. That's our sample space. We need to assign a probability law. for lack of imagination, I'm taking the probability law to be the area of a subset. So if we have two subsets of the sample space that have equal areas, then I'm postulating that they are equally likely to occur. The probability that I fall here is the same as the probability that I fall there. The model doesn't have to be that way. But if I have sort of complete ignorance of which points are more likely than others, that might be the reasonable model to use. So equal areas mean equal probabilities. If the area is twice as large, the probability is going to be twice as big. So this is our model. We can now answer questions. Let's answer the easy one. What's the probability that the outcome is exactly this point?
So say, yeah, the probability of 0.5, 0.3. Well, 0.5, 0.3 has an area of 0. So the probability of something with area is equal to 0 is equal to 0.
That, of course, is 0, because a single point has 0 area. And since probability is equal to area, that's 0 probability.
Oh.
Area, and since probability is equal to area, that's 0 probability. How about the probability that the sum of the coordinates of the point that we got is less than or equal to 1/2? How do you deal with it?
So before we drew this, oh, you can adjust the volume by doing up or down? The heck? That's weird.
Is the same as the procedure.
So probability that the sum is less than or equal to 1/2. So if you get, say, x, if you get like 1/2 and 0, that's here. If you get 0 and 1/2, that's here. If you get like 1/4 and 1/4, that's like right here. And so the whole kind of is less than or equal to 1/2. So these are kind of like at the edge. And then all these points are in there. And so what's the area of this? Well, you can kind of think of it. It's, this whole thing is 1/4 and then it's 1/2 of that. So it should be an 1/8.
Would follow in continuous probability problems. Where x plus y equals to 1 equal to 1/2. How do you deal with it? Well, you look at the picture again, at your sample space, and try to describe the event that you're talking about. The sum being less than 1/2 corresponds to getting an outcome that's below this line, where this line is the line where x plus y equals to 1/2. So the intercepts of that line with the axis are 1/2 and 1/2. So you describe the event visually, and then you use your probability law. The probability law that we have is that the probability of a set is equal to the area of that set. So all we need to find is the area of this triangle, which is 1/2 times 1/2 times 1/2 equals to 1/8.
Area of a triangle. Yeah, it's this times 1/2. Yeah,
okay.
Makes sense.
Moral from these two examples is that it's always useful to have a picture and work with a picture to visualize the events that you're talking about. And once you have a probability law in your hands, then it's a matter of calculation to find the probabilities of an event of interest. The calculations we did in these two examples, of course, were very simple. Sometimes calculations may be a lot harder, but it's a different business. It's a business of calculus, for example, or being good in algebra and so on. As far as probability is concerned, it's clear what you will be doing, and then maybe you're faced with a harder algebraic part to actually carry out the calculations. The area of a triangle is easy to compute. If I had put down a very complicated shape, then you might need to solve a hard integration problem to find the area of that shape. But
integration problem, like this shape right here, you would use integration for that? Maybe if you kind of like drew a line through it, and then you could like describe this function as like f of x, and then this function down here is like g of x. Then if these two, if this is like a and b, then it'd be like the integral of f of x dx from a to b plus I think it'd be like negative g of x times dx from a to b. Is that what he means by difficult integration problem? You'd have to characterize this shape by f and g, maybe.
Stuff that belongs to another class that you have presumably mastered by now. Good. Okay, so now let me spend just a couple of minutes to return to a point that I raised before. I was saying that the axiom that we had about additivity might not quite be enough. Let's illustrate what I mean by the following example. Think of the experiment where you keep flipping a coin and you wait until you obtain heads for the first time. What's the sample space of this experiment? It might happen in the first flip, it might happen.
Yeah, wait until you see X for the first time. Yeah, I mean, it'd basically be like the outcomes would be 1 to, basically up to infinity.
In the 10th flip, heads for the first time might occur in the millionth flip. So the outcome of this experiment is going to be an integer, and there's no bound to that integer. You might have to wait very much until that happens. So the natural sample space is the set of all possible integers. Somebody tells you some information about the probability law. The probability that you have to wait for n flips is equal to 2 to the minus n. Where did this come? That's a separate story. Where did it come from? Somebody tells it to us, and they ask, and those probabilities are plotted here as a function of n, and you're asked to find the probability that the outcome is an even number. How do you go about calculating that probability?
Probability that it's an even number. So, I mean, it'd pretty much be the probability, and we're dealing with outcomes here. So the probability that the event happens, the event that n is even. So the event where n is even is when we have the outcome 2, 4, 6, 8. Basically this. So yeah, I mean, it's basically, which equals the probability, as he said here, probability of 2 plus probability of 4 plus, it's equal to, 1 over 2 to the, 2 to the 2 plus 1 over 2 to the 4th plus, 6. Yeah, and I guess, equals a third.
Are plotted here as a function of n, and you're asked to find the probability that the outcome is an even number. How do you go about calculating that probability? So the probability of being an even number is the probability of the subset that consists of just the even numbers So it would be a subset of this kind that includes 2, 4, and so on.
It's an interesting way to draw it. Like you could kind of draw the sample space where it's kind of like a grid, you know. So you got like 1, you got 2, 3, 4, 5, 6. But the problem is, if you want to draw this, like it would have to be like infinitely, you know, squished kind of, because like this whole thing has to sum up to 1. So yeah, it's kind of weird.
So any reasonable person would say, well, the probability of obtaining an outcome.
Another way to kind of like draw this too is that, so we have kind of like the sample space. And so the kind of event 1 kind of takes up like this much space. And then, you know, the event 2 kind of has like this much space. And then like the event 3 has like this much space. And then the event 4 has this much space. And then blah, blah, blah. And then blah, blah, blah. I feel like I maybe even drew it too high. It's like if you just kind of wanted to draw it as kind of like the grid thing. Okay, fine. Yeah, we'll just close it. So yeah, we'll say 1, 2, 3, 4. Is that right? I mean, the probability of 1 is like 1/2. Probability of 2 is 1/4. Probability of 3 is 1/2 to the 3, 1/8. So it's like, so we're dealing with this whole thing, and we take half of that, and then we're dealing with like this half, and we take half of that, and we're dealing with this half, we take half of that. 1/8, 1/16. So it kind of looks like this. You got 5, and then the dot thing. Maybe drawing it as a tree as well. You got kind of like, we got 1, and then we got kind of like everything that's like not 1. And so say here we got like 2, and here everything that's like not 2, and then here we got like 3, and then everything's not 3, and then we got 4, and then like everything that's not 4. Probability of this is like 1/2, and then the probability, I guess this is like 1/2, and then this is like 1/2, and this is like 1/2, this is like 1/2, this is like 1/2, it's like 1/2. Yep.
Either 2 or 4 or 6 and so on, is equal to the probability of obtaining a 2 plus the probability of obtaining a 4 plus the probability of obtaining a 6 and so on. These probabilities are given to us. So here I have to do my algebra. I add this geometric series and I get an answer of 1/3. That's what any reasonable person would do. But a person who only knows the axioms that I posted just a little earlier may get stuck. They would get stuck at this point. How do we justify this?
Oh, yeah, I said the finite set thing before.
We had this property for the union of disjoint sets and the corresponding property that tells us that the total probability of finitely many things, outcomes, is the sum of their individual probabilities. But here we're using it on an infinite collection. The probability of infinitely many points is equal to the probability.
Just wanted to make one note about another class that I might stream at one point. Theory of computation class. Yeah.
to the sum of probabilities of each one of these. To justify this step, we need to introduce one additional rule, an additional axiom that tells us that this step is actually legitimate. And this is the countable additivity axiom, which is a little stronger or quite a bit stronger than the additivity axiom we had before. It tells us that if we have a sequence of sets that are disjoint and we want to find their total probability, then we are allowed to add their individual probabilities.
Axiom.
So the picture might be such as follows. We have a sequence of sets, A1, A2, A3, and so on. I guess in order to fit them inside the sample space, the sets need to get smaller and smaller, perhaps. They are disjoint. We have a sequence of such sets. The total probability of falling anywhere inside one of those sets is the sum of their individual probabilities. A key subtlety that's involved here is that we're talking about a sequence of events. If, by sequence, we mean that these events can be arranged in order. I can tell you the first event, the second event, the third event, and so on. So if you have such a collection of events that can be ordered as first, second, third, and so on, then you can add their probabilities. You can find the probability of their union. So this point is actually a little more subtle that you might appreciate at this point, and I'm going to return to it at the beginning of the next lecture. For now, enjoy the first week of classes and
Nice.
have a good weekend.
Bet. Let's go. Yeah, we can start the next lecture. Why not? Feeling it. Let's go.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So here's the agenda for today. We're going to do a very quick review, and then we're going to introduce some very important concepts. The idea is that all information is always partial. And the question is, what do we do to probabilities if we have some partial information about a random experiment? We're going to introduce the important
partial information about the random experiment. So you've got your experiment here. You know, it just produces an outcome, which is in sample space, which is equal to, you know, O1, O2, say talking about finite ones. So, you know, it's something like, yeah, it's almost something like we have all our outcomes and the partial information might be like, all right, one of these outcomes occurred. Or like we know these outcomes did not occur. This event occurred. So now we can ask questions about further events. Like, oh, now that we know that this event occurred, what's the probability of something what's the probability of some event happening over here? Well, that's, you know, equal to 0. What's the probability of some event happening over here? Well, it's greater than the probability of whatever this like initial event thing was. Greater than that. Sample space, you know, you've got, yeah, so we'll say, you know, we got all these events and we'll say, all right, we know, you know, this happened. So what's the probability of this event, or what's the probability of this event, or this event, or this event? Just a quick thing. If we know that this happened and we say, what's the probability of this event? It's not a 1 because, like, you know, one outcome could have occurred out here. So it's not 1. But I guess another thing with partial information is if we have like a tree describing all the outcomes and we say, we know that, you know, like this, we know that, you know, I don't know, this event occurred. Say we know that like this event occurred. We can just basically chop off this part of the tree. And so we're just left with this part of the tree. So we just kind of like look at this. This is almost essentially our new sample space. It's kind of like you're starting with the sample space and then you subtract away, you know, part of it and you get, you know, the sample space with just A sort of like left in it. And this is kind of like your new sample space that you're dealing with. So everything's kind of relative to this new sample space.
Of conditional probability. And then we will see 3 very useful ways in which it is used. And these ways basically correspond to divide and conquer methods for breaking up problems into simpler pieces. And also one more fundamental tool which allows us to use conditional probabilities to do inference. That is, if we get a little bit of information about some phenomenon, what can we infer about the things that we have not seen? So, our quick review. In setting up a model of a random experiment, the first thing to do is to come up with a list of all the possible outcomes of the experiment. So that list is what we call the sample space. It's a set, and the elements of the sample space are all the possible outcomes. Those possible outcomes must be distinguishable from each other. They're mutually exclusive. Either one happens or the other happens, but not both. And they're collectively exhaustive. That is, no matter what, the outcome of the experiment is going to be an element of the sample space. And then we discussed last time that there's also an element of an art in how to choose your sample space, depending on how much detail you want to capture. This is usually the easy part. Then the more interesting part is to assign probabilities to our model. That is, to make some statements about what we believe to be likely and what we believe to be unlikely. The way we do that is by assigning probabilities to subsets of the sample space. So as we have our sample space here, we may have a subset A, and we assign a number to that subset, P of A, which is the probability that this event happens.
Got like A. And we assign P of A to this. And we got like B. And we assign like P of B to this. Kind of like A. And we assign P of A. We got like B. Assign P of B.
This is the probability that when we do the experiment and we get an outcome, it's the probability that the outcome happens to fall inside that event. We have certain rules that probabilities should satisfy. They're non-negative. The probability of the overall sample space is equal to 1, which expresses the fact that we are certain, no matter what, the outcome is going to be an element of the sample space. Well, if we set it...
Probability that equals to 1. And so like, what does the probability of an event mean? Probability that this event occurs means that the outcome is in this event. It's kind of like we have the sample space and say we have like some event A, and like we run the experiment, and it's like boom, it's like that event occurs. So it's kind of like, how likely do we think that the event is gonna be inside A versus outside of A, and we assign that number to it. I guess the frequentist thing is like, oh, if we like ran a bunch of experiments, then we kind of like over the long run, the number of times it kind of comes up A is going to be equal to, the probability of A, versus we don't know what's going to happen. We're about to do it. How likely do we think the event's going to be in A, basically? It seems.
Right, so that it exhausts all possibilities, this should be the case. And then there's another interesting property of probabilities that says that if we have two events or two subsets that are disjoint, and we're interested in the probability that one or the other happens, that is, the outcome belongs to A or belongs to B. For disjoint events, the total probability of these two taken together is just the sum of their individual probabilities. So probabilities behave like masses. The mass of the object consisting of A and B is the sum of the masses of these two objects. Or you can think of probabilities as areas. They have, again, the same property. The area of A together with B is the area of A plus the area of B. But as we discussed at the end of the last lecture, it's useful to have in our hands a more general version of this additivity property, which says the following. If we take a sequence of sets, A1, A2, A3, A4, and so on, and we put all those sets together, it's an infinite sequence, and we ask for the probability that the outcome falls somewhere in this infinite union. That is, we are asking for the probability that the outcome belongs to one of these sets. And assuming that the sets are disjoint, we can again find the probability of the overall set by adding up the probabilities of the individual sets. So this is a nice and simple property, but it's a little more subtle than you might think. And let's see what's going on by considering the following example. We had an example last time where we take our sample space to be the unit square. And we said, let's consider a probability law that says that the probability of a subset is just the area of that subset. So let's consider this probability law. Okay. Now the unit square is the set, let me just draw it this way. The unit square is the union of one element sets consisting of all the points. So the unit square is made up.
Is it of all the points? I mean, what if it's continuous? I don't know. Is it?
By the union.
All right, the finite
of
thing.
the various points inside the square. So union over all x's and y's, okay? So the square is made up out of all the points that it contains. And now let's do a calculation. One is the probability of our overall sample space, which is the unit square. Now, the unit square is the union of these things. Which, according to our additivity axiom, is the sum of the probabilities of all these one element sets.
Yeah.
Now, what is the probability of a one element set? What is the probability of this one element set? What's the probability that our outcome is exactly that particular point? Well, it's the area of that set, which is 0. So it's just the sum of zeros. And by any reasonable definition, the sum of zeros is 0. So we just proved that 1 is equal to 0. Okay, either probability theory is dead, or there is some mistake in the derivation that I did. Okay, the mistake is quite subtle, and it comes at this step. We sort of applied the additivity axiom by saying that the unit square is the union of all those sets. Can we really apply our additivity axiom? Here's the catch. The additivity axiom applies to the case where we have a sequence of disjoint events and we take their union. Is this a sequence of sets? Can you make up the whole unit square by taking a sequence of elements inside it and cover the whole unit square? Well, if you try, if you start looking at a sequence of one element points, that sequence will never be able to exhaust the whole unit square. So there's a deep reason behind that, and the reason is that infinite sets are not all of the same size. The integers are an infinite set, and you can arrange the integers in a sequence, but a continuous set like the unit square is a bigger set. It's so-called uncountable. It has more elements than any sequence could have. So this union here is not of this kind where we would have a sequence of events. It's a different kind of union. It's a union that involves a union of many, many more sets. So the countable additivity axiom does not apply in this case because we're not dealing with a sequence of sets. And so this is the incorrect step. So at some level, you might think that this is puzzling and awfully confusing. On the other hand, if you think about areas the way you're used to them from calculus, there's nothing mysterious about it. Every point on the unit square has zero area. When you put all the points together, they make up something that has finite area. So there shouldn't be any mystery behind it. Now, one interesting thing that this discussion tells us, especially the fact that a single element set has zero area, is the following. Individual points have zero probability. After you do the experiment and you observe the outcome, it's going to be an individual point. So what happened in that experiment is something that initially you thought had zero probability of occurring. So if you happen to get some particular numbers and you say, well, in the beginning, what did I think about those specific numbers? I thought they had zero probability, but yet those particular numbers did occur.
So that implies that the probability of some event A is equal to 0 does not imply that A is impossible. There's a 0% chance that A will happen. Oh, boom, A happened. Oh, dang. Well, probability of 0 events happens sometimes. You know, shit happens. Is there kind of like a counter thing? Like if we say like the probability of A is equal to 1, then can it be the case that A doesn't happen? I think you can. I think if you took like the unit square and you said that A is basically the unit square minus, the point, 0.5, 0.3, just minus like a single point. I mean, this has a probability, this has an area of 1 and this has an area of 0. So, I mean, the probability of A is going to be equal to 1, but it still is possible that you do hit this exact point right here. And so, it is possible that if something has a all these sets have a probability of 1. If you there's like an infinite number of events which have a probability of 1. So you can have probability of 1 and then that event does not occur. Kind of similar way.
So one moral from this is that zero probability does not mean impossible. It just means extremely, extremely unlikely by itself. So zero probability things do happen. In such continuous models, actually zero probability outcomes are everything that happens. And the bumper sticker version of this is to always expect the unexpected. Yes?
Sorry, but it's just very, very, very close to zero.
Well, so probability is supposed to be a real number, so it's either 0 or it's a positive number. So you can think of the probability of things just close to that point, and those probabilities are tiny and close to 0. So that's how we're going to interpret probabilities in continuous models, but this is 2 chapters ahead. Yep.
Interpret probability of 0 in continuous models that way, then how do we interpret probability of 1? That it's extremely likely, but not necessarily for certain.
That's also the case. For example, if you ask in this continuous model, if you ask me for the probability that xy is different than the point 0, 0, this is the whole square except for 1 point. So the area of this is going to be 1. But this event is not entirely certain because the 0, 0 outcome is also possible. So again, probability of 1 means essential certainty, but it still allows the possibility that the outcome might be outside that set. So these are some of the weird things that are
It's just, that's so weird because, yeah, I mean, you could kind of have the probability of the square, but then like subtract away an infinite number of individual points. It's fucking weird, man.
when you have continuous models.
It's broken.
And that's why we start this class with discrete models on which we will be spending the next couple of weeks. Okay, so now once we have set up our probability model,
Okay.
and we have a legitimate probability law that has these properties, then the rest is usually simple. Somebody asks you a question of calculating the probability of some event. Well, you were told something about the probability law, such as, for example, that probabilities are equal to areas, and then you just need to calculate. In this type of examples, somebody would give you a set, and you would have to calculate the area of that set. So the rest is just calculation and simple. All right, so now it's time to start with our main business for today. And the starting point is the following. You know something about the world, and based on what you know, you set up a probability model and you write down probabilities for the different outcomes. Then something happens and somebody tells you a little more about the world, gives you some new information. This new information in general should change your beliefs about what happened or what may happen. So whenever we're given new information, some partial information about the outcome of the experiment, we should revise our belief.
Another kind of way to draw that would be like if we have a sample space of these kinds of events, like 2, 3, like 1, 2, 3, 6, whatever, and then we say that, you know, this side did not happen and this side definitely did happen, then we can kind of update the probabilities.
And conditional probabilities are just the probabilities that apply after the revision of our beliefs when we're given some information. So let's make this into a numerical example. So inside the sample space, this part of the sample space, let's say, has probability 3/6. This part has 2/6, and that part has 1/6. I guess that means that out here we have 0 probability.
So a better way to kind of draw this would be like, so this is half. So you got basically like all of A is kind of half, and then B is half as well. Oh, wait a minute. Actually, it's not the case that A is 1/2. It's the case that A minus B is 1/2. But then kind of A kind of stretches all the way out here to like 5/6. It's kind of like A is like 5/6. Guess this is like A and B. And so here is just like B minus A. And then, this is also like B and A in here. This is A. B is like this. Another way to kind of like draw this is so we got kind of like A. Let's say that A is red, B is blue. Maybe we'll say A is green. So this is like A, and then I don't know, whatever, like kind of overlap here. This is kind of like all together. It's kind of another way to draw it.
These were our initial beliefs about the outcome of the experiment. Suppose now that someone comes and tells you that event B occurred. So they don't tell you the full outcome.
All right. Peace out, guys, for the stream. That was fun. That was a great time. I had fun. If you made it this far, thanks for hanging out. This is cool. See you guys next time. Later. Peace.